This is a lesson on properties of exponents. So this briefly goes over several different properties for exponents. So let's just kind of look at an exponential term and what that looks like. So this is an example of an exponential term, and I'm going to break it apart by pieces. So this a value is called a coefficient. And it'll be a number, like a constant, like 2, 3, 4. And it's in front of a variable that serves as the base with this little script, superscript is what they call it, that is the exponent or power. We'll use exponent. The definition of an exponent is the number of times the base is multiplied. So n up here indicates the number of times that the base is multiplied, just the base. So if we had, for example, 2 to the third, this 3 indicates the number of times that 2 is being multiplied. So it's 2 times 2 times 2, which simplifies to 4 times 2, which is 8. So we can use this definition of an exponent to help us simplify these expressions. So the multiplication property is the first one we're going to cover, and it only works, you can only apply this when the bases are the same. So in example 1 here, you can see that the bases are all x, and I'm going to show you this the long way. I'm going to expand it out the long way, and then I'll explain the property to you after I've done that. So I'm going to use the definition of an exponent. I know that x squared is x times x because the exponent indicates the number of times that the base is multiplied. And then x to the fourth is 1, 2, 3, 4. And then x to the third is 1, 2, 3. I'm actually going to do this in a different color so you can see that they represent different terms. Even though they're different colors, they are still x. So if I can collapse using the definition of an exponent, I now have 1, 2, 3, 4, 5, 6, 7, 8, 9 x's being multiplied. So I can collapse using the definition of exponent, and I can say that x squared times x to the fourth times x to the third is x to the ninth. Let's explore that for a second and focus on these exponents. Can you think of a way we can use these exponents to come up with 9? If you look down at what I did here, I technically added them all up. So if we look at 2 plus 4 plus 3, those were the exponents, we get 9. So we can summarize this by saying, in general, when you multiply exponential components with the same base, you're actually just adding the exponents. You can skip straight to here from here. You don't have to draw all this out. You can if you want to, but it is a little time consuming, especially if you have like x to the 15th. Let's do another example like that just to show you. We have 2x to the 3rd times 6x to the 7th. The bases are the same, so we can collapse this. We can simplify this. And then we have coefficients. So 2x to the 3rd times 6x to the 7th, what we're going to do is multiply these coefficients. I'm going to use my commutative property. And the exponential terms. So all I've done here, I've not changed anything. I've just used my commutative property, which means that I've changed the order. This is all multiplication. 2 times x to the 3rd times 6 times x to the 7th. So it's all joined by multiplication, which means that I can change the order, and that's okay. You don't have to change the order. I'm just showing that I'm going to be multiplying the coefficients, and I'm going to be adding the exponents on the exponential terms. So this equals 12x to the 10th. So I kind of skipped out from expanding this. If you're a little lost, then you can go ahead and expand it. X to the 3rd times x to the 7th. You can see how that's a little time consuming. And then if we collapse it, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's where that x to the 10th comes from. And then this flows nicely into the division property of exponents. And I'm going to kind of bring you through the same process. I'm going to expand it out first. X to the 5th times y to the 3rd over x squared times y. And I kind of spaced it out because I'm intending to kind of group these x's and group these y's. You don't have to space it out like that. I'm just doing it for teaching purposes. So we know, let's back this up. We know that if we have, for example, 2 over 2, that divides to 1. So we can use that same concept here. These are all being multiplied together. So we can start dividing out common terms, not dividing out, dividing to 1 common terms, and kind of clear up some of these components. And then what we're left with is our solution, is our simplified expression. So we're left with x to the 3rd y squared. Now, we know that expanding it can be time consuming. It is effective, but time consuming. So let's take a look at these exponents and see if you can notice a pattern. If I have a 5 in the top and a 2 in the bottom, how can I manipulate those numbers to get a 3? And if I have a 3 in the top and a 1 in the bottom, how can I manipulate those numbers to get a 2? So instead of adding when we have multiplication, when we have division, we're actually subtracting. Let's take a look at the next example to just see if it works. I'm going to use some of the same methods I used in the previous example up at the top. I'm going to group my like components like this. I didn't change any orders, I just grouped them. And then I'm going to use my shortcut to help me simplify, we do actually divide 6 and 2. 6 divided by 2 is 3. And then here, this is a 1. It's not written, but it is a 1. We're going to use the shortcut, and if you notice when I circled that, it kind of looks like 3 minus 1. Kind of. Which is 2. And then with the y's, we're going to use our shortcut. This would be a 1 right here. So we're going to do 8 minus 1 to get y to the 7th. And again, if you prefer, you can expand it out to see that we get x squared here. Y to the 8th is a little more involved. 5, 6, 7, 8. And that's where y to the 7th comes in there. You can always do that to check yourself if you want. Next page. Power raised to a power. So when I say that, it means I have an exponent and it's raised to another exponent. And so when I see that, I usually call it power to a power. Let's expand it out. We have x to the 3rd is the base. Nope, I'm sorry. X to the 6th is the base of this exponent. So that means that it's x to the 6th 3 times, by definition. And then even further than that, x to the 6th, 1, 2, 3, 4, 5, 6. There's another one. 1, 2, 3, 4, 5, 6. And another one. It's a little tedious. Okay? And then we know from previous examples that we can just total these. We can add them all up. 6, 12, 18. Total x's. So let's look at the numbers here. How can we use 6 and 3 to make 18? What operation could we do to make 18? And that would be multiplication. So power to a power means multiply. Oh, here's a big one. This is kind of cool because we're going to use another property that we didn't see in the previous example. Basically, you can do this 2 ways. You can write it out like I did here 3 times. So we can write this parentheses 3 times. Or you can kind of use the distributive property on each component. So I'm going to write it that way, just so you can see both methods. X to the 4th to the 3rd, y to the 3rd to the 3rd, z to the 3rd. So I've distributed this power because I know that, let me just show that really quick. Erase this so you can see it. By definition, this is saying 3x to the 4th, y to the 3rd, z 3 times. Means that there's going to be 3 to the 3rd, x to the 4th to the 3rd, y to the 3rd to the 3rd. So that's why that works. And then we're going to simplify that. 3 to the 3rd means 3 times 3 times 3, which is 27. Power to a power means multiply. Power to a power means multiply. And then this one just gets applied. So you might be wondering here why I got 27 instead of 9. Why didn't I multiply? Well, because when it's a constant like 3, 3 to the third means 3 times 3 times 3, which is 9 times 3, which is 27. So you have to be careful there. Then we'll move on to a zero exponent. Anything raised to a zero power is 1 by definition, which seems a little odd. Something raised to a zero exponent would be 1. And the easiest way I've seen to explain this is by using place value. So let's look at this for a second. We have the case of a zero exponent, and we have a case of a negative exponent, which we haven't actually looked at yet, but we will in this lesson. So this is kind of an introduction to a zero exponent and negative exponents. So you might think a negative exponent means that it's a negative number, but it's actually just a place value. So if we explore 10, 10's an easy number, to different powers. So 10 to the 0 we know is 1. 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000. And then symmetrically, if we go on the other side, this is just a decimal. 10 to the negative 1 would be tenths. 10 to the negative 2 would be hundredths, and so on. So the exponent indicates whether it's a whole number or a fraction or a decimal, kind of. I always thought that was kind of neat. So let's use that here to test it out on a few. Anything to a zero power is just 1. Here we have x to the 0, which is 1, but we have a negative out front. Pay attention here, we have x to the 0, which is 1, but we have a 2 multiplied by it. And then in this case we have 2x all raised to the 0, which is 1, because the whole thing is raised to the 0. So you have to pay attention to what is the base. We're going to use the zero power to help us discover talk about the negative exponents. So we did talk about on the previous page that a negative exponent indicates a fraction or a decimal, not the sign of the number. So if we start with 1 over x to the n, we do know that 1 is the same as x to the 0, because I want to use the same base. We also know a division property, and then we can simplify. So what this is saying is that if we have a fraction, it's the same as a negative exponent. Isn't that so pretty, how that works out? So we can flip-flop that, and if we start here, we can end there without doing all this, because we know this to be true. So for example, number 8, y to the negative 8, this negative exponent indicates that it is a fraction, and as a fraction, it becomes a positive number. And then number 9, the negative is in the bottom, so it's kind of like a reciprocal. If we move it to the top, it becomes positive. So it seems kind of tricky. When you're moving it over the fraction bar, it's changing the sign, but I want to show you the mathematics behind that because it is important. It's not magic, it's math. I added an x to the 0 here because it is just a 1 and 1 won't change it. Now I'm going to use my properties of exponents. And what I did here is I subtracted these exponents, minus -4. And we know that minus a negative becomes a positive. Dun, dun, dun. So that's a long way of doing it. You can do that if you want to. That is mathematically correct. But essentially the shortcut is if you see a negative exponent, move it over the fraction bar and it becomes positive. A negative exponent should never be left in the answer. A simplified answer has all positive exponents. I hope you enjoyed the lesson. That's all I have for today. If you have any questions, please email me.